Good evening and welcome to your Chapter 13 notes. Tonight we are going to look at colligative properties. These are properties that depend on the concentration of the solute particles, but not their identity. So we don't care what we're adding into our water or our solution. What we're looking at, though, is how much of it are we adding? So what does that do to the property of our solution? So when a non-volatile, non-electrolyte solute is added to a solvent, it's going to raise the boiling point, lower the freezing point, and it's going to lower the vapor pressure. So what do we mean by non-volatile, non-electrolyte? Basically, non-electrolyte, it doesn't produce ions. So when you break it down, it's not going to have a lot of positive, negative, that it won't really carry a current through. Non-volatile, meaning it doesn't easily vaporize or turn into a gas. So let's begin looking at the idea of vapor pressure lowering. So what is vapor pressure? This is the pressure caused by molecules that escape the liquid phase and enter the gaseous phase. So again, if we have our beaker of liquid, there are particles at the surface of this liquid that are going to come off and turn into gas. However, a non-volatile solute that is added lowers the concentration of the liquid molecules at the surface of the liquid. So basically, this is what it looks like. Here is a pure liquid. Over here is the liquid plus the solute that has been added to it. So here's our little solute particles, and here are our liquid. You can see there is much less liquid little circles here than we have over here. So in a pure liquid, any of these could be changed into a gas. So you can see we have almost twice as much. Over here, only your liquid is going to change into the gas. So it's separating these liquid molecules, making less at the surface, so it's going to lower the vapor pressure because you have less going in. So the tendency of liquids to want to change to the gas phase is lowered, so we lower the vapor pressure. The last one we're going to look at tonight is osmotic pressure. So let's look at osmotic pressure. Osmotic pressure has to do with osmosis. Osmosis you should be semi-familiar with because I'm sure you talked about it last year in biology. This is defined as the movement of solvent through a semi-permeable membrane from the side of lower solute concentration to the side of higher solute concentration. So if we look at here at this example, here's going to be our semi-permeable membrane. So it's going to allow some particles through, but not all. The white particles are going to be our solute, and our blue is going to be our solvent. So now, if you wanted to pick which way you think these are going to move, we'll look at the concentration. This one has fewer solute, so your concentration is going to be lower. Here we've got a higher concentration of solute. So to even them out, get into that equilibrium state that everything likes to be in, which way should we move? Well, we will move over. And of course, then this guy won't go all the way out. He will stay in. Just the magic of running this on different computers. So what does it mean to be semi-permeable? Well, it's going to allow the movement of some particles while blocking the movement of others. We know that not every particle has the same exact diameter. We learned that when we talked about our periodic properties. So some are going to move through and others are not. Again, it works much better on my other computer when I tried it earlier. So basically, these did not go through. They would stop at the semi-permeable membrane and stay on the side that they started at. All the little blue ones, they started over here, but they were able to pass through our semi-permeable membrane. So when we talk about osmotic pressure, this is going to be then the pressure needed to be applied so that osmosis doesn't happen, so that we don't have these particles moving through the membrane. So the greater concentration we have in the solution, the greater the osmotic pressure we're going to need. What we find is that when this happens, the cells in higher concentrated solutions will shrink because everything will come out of them. So you can think of the concentration out here being greater concentration. In here it's smaller, so anything that's in here is going to move out. As the liquid moves out, this will shrink. But cells in lower concentrated solutions will swell because you're going to have exactly the opposite. Out here is smaller. In here is greater. So remember, we move from greater or from smaller to greater. So we're going to have more liquid going inside of the cell, so it is going to increase.